So to begin the screencast for the second week, this week is on the electric field. So part one of the screencast will be on the theory. We know from last week, like charges repel and unlike charges attract. So if we had a system with two charges plus Q and minus Q, and a third charge little q, well, then there would be two forces on the smaller charge. It would be repulsion from plus q and attraction to minus q, and then the net force on the smaller charge would be the sum of those two forces, this force F. Now, the idea of field theory is this. The force is not action at a distance. Rather, there exists a force field. We call it the electric field. We'll use the notation E for electric field. And at any point in the space, there's a value of the electric field. So the electric field extends throughout the whole volume of space. It's associated with the charges, capital Q, negative capital Q, smaller q. Each one of these charges has an associated electric field, and the combined electric field is defined everywhere throughout the space. I draw it here in two dimensions, but this would even be in 3 dimensions. So at every point x in the volume, there's a field vector, E of x. So if I take any point in the space, let's say here, there'll be a field vector. Let's say pointing more or less in this direction. Well, not exactly pointing towards negative Q. It's a little bit pointing away from capital Q, although the force towards negative Q is stronger. So maybe it would be off in this direction somehow. That would be E at the point X. And remember, E is a vector. So the field, what we call the field, or the electric field, is a vector function of position in 3 dimensions. Now, according to field theory, the field is not just a mathematical construction. The field is something physically real. In particular, it has a form of energy called field energy. And we'll study field energy later. All right, so there are 2 things we need to know. First of all, what's the definition of the electric field? It's a force field. So how is it related to forces? And secondly, how is it created? It's associated with charges. So how do charges create the electric field? Well, that's what we're going to study in this screencast. Now, I recommend that you take notes because the equations we'll write down will be necessary for the homework problems. So suppose we have two charges. Let's just consider a system of two charges. A positive charge and a negative charge. And the positive charge has an electric field that points away from the positive charge. The negative charge has an electric field that points toward the negative charge. And we'll write down the equation for the fields in a minute. And now, throughout the space, at all points within this space, there are field vectors. So if I come out to a point here, there'll be a field vector. It'll be directed sort of in this direction. And the electric field lines give you a way of visualizing the field. They're a set of curves with the property that at every point, the curve is tangent to the field vector at that point. So close to the positive charge, the field points away from a positive charge, and the field line will be directed away from the positive charge. And on the other hand, near a negative charge, the field will point towards the negative charge, and the field line will be in that direction, tangent to that direction. So this gives you a sort of a picture of the field. All right, so the idea of field theory is that the electric force is exerted by the field, not by the sources of the fields. So in this system, you have two charges, a positive charge and a negative charge, and those are the sources of a field. And if there were a third charge somewhere in this space, it would experience a force that's exerted by the field at its position, not by the sources which are far away. So, according to field theory, the electric force is not action at a distance. It's exerted by the field at the location of the particle experiencing the force. Now, the definition of the electric field is that if a test charge Q is placed at a position X, then the electric force on Q is Q times E of X. This is the definition of E of X. If I put a test charge someplace, let's say I put a test charge here, and I observe its force, perhaps by watching its acceleration, I'll know the force that's acting on it. Maybe it's in this direction. And the electric field is the force divided by the charge. So in other words, E of X is equal to the force per unit charge on a test charge located at X. Now, E of X exists whether the test charge is present or not. This just gives me a way of measuring E of X. So the electric field exists everywhere. If there happens to be a charge at some point, it will experience a force in the direction of the value of its charge times the electric field. But the electric field doesn't depend on this charge. The electric field exists at this point. This is some arbitrary point X. The electric field exists at that point, whether there's a test charge there or not. I can think of the test charge as a little probe for observing the field. And the electric field is the force per unit charge on that probe. But the electric field exists even if there is no probe present. It exists because of these two sources. Or in a more complicated system, whatever sources are present. Well, that tells us the definition of the electric field, and in particular, the unit of the electric field. What's the unit of electric field? Well, electric field is force per unit charge. So it's force, that's newtons, divided by charge, that's coulombs. So one way to define the unit of the electric field is newtons per coulomb. It doesn't have any special name, it's just newtons per coulomb. Later, when we introduce the idea of the electric potential, there'll be a different way of expressing the unit for the electric field in terms of volts. The electric field is not volts, it's volts per meter. All right, so now, let's summarize what I've said so far. So here's a picture of a field coming from two sources, 2 point charges. The field fills a volume of space. It's present at every point in the space. At every point in the space, there's a field vector, E of x. If a charge particle is placed at some point, let's call the point C, then there'll be a force on that particle. And the force will be equal to Q times the electric field. So we call the electric field a force field. It exerts forces on charges. And the strength of the force is the charge in coulombs times the field at the position of the charge. So the force is exerted by the field at the point X, not by the distant sources. So it's not action at a distance. The electric field, the electric force is a field effect. It's not action at a distance. Know the definition of the electric field, we can address the second question, which is, what is the electric field produced by a source? And let's take the source to be the simplest possible source, a single charged particle. So suppose we have a charged particle Q. Let's keep it simple by saying it's positive. And it has to have some position in space, so let's call its position x sub q. Position vector x sub q is the position of q. That has to be a three-dimensional vector. And now what we want to answer is, what is the electric field at some other point x? Some other arbitrary point x. So here's the source. It's at x equals 2, y equals 1, z equals 0 in 3 dimensions. I just draw it in 2 dimensions here. So it has 3 coordinates, x, y, z. Well, x sub q, y sub q, z sub q. Or it's got a position vector relative to the origin of the coordinate system, x sub q. And of course that has to be a vector. So I have to draw an arrow over it. That's the source. Now, what's the electric field at x? Well, where is x? Well, anywhere I want. So let's say, what's the electric field at this point right here? Let's consider that point. Well, I would insert a little test charge at that point, like a probe. And the electric field at that point is the force on the test charge divided by the charge of the test charge. Now I know the force on the test charge from last week. I know the force on the test charge from Coulomb's law. The force on this little charge, let's call this charge Q, located at x, is Q times Q over 4 pi epsilon 0, r hat over r squared. That's Coulomb's law. Coulomb measured that force. It's the product of the two charges, little q and positive q, capital Q, times r hat over r squared. R hat gives it the direction away from the source. R squared, it's an inverse square law, times a universal constant, which sometimes we call K, Coulomb's constant, or sometimes we call it 1 over 4 pi epsilon 0. 1 over 4 pi epsilon 0 is the same as K. So there's the force. And the field is that force divided by Q. Not the Q of the source, the Q of the probe. Well, now you see what happens. The Q of the probe, lowercase q, cancels. So this is the electric field at the point X. It doesn't depend on the test charge because it's the ratio of the force divided by the test charge. And the force is proportional to the test charge. So when I take the ratio, I get something that doesn't depend on the test charge. In fact, at this point, I could say take the limit that the test charge goes to 0. I'd have the same electric field because the electric field just doesn't depend on the test charge. So see, the electric field is defined by the sources. In other words, I can write it in terms of the sources. I may define it in terms of a probe, but the theory gives me a formula for the electric field at any point within this volume that only depends on the sources. Now, I've written it here for one source, but obviously if I had many sources, I would just use the superposition principle because I can superimpose the forces on the test charge from all the different charges within the system. When I divide out the test charge, it cancels, and I just get a sum over all the sources. So this is the electric field for one particle, one source with charge Q. Now what's R? R is x minus xq. If I think back to the force, R is the vector from the charge capital Q to the charge little q. It's x minus xq. So R here is the vector x minus xq. X is the point where I'm measuring the electric field. XQ is the point where this source is located. Okay? So if I have a source and I have some point where I'm interested in the field, R would be the vector from this source, let's say it has charge Q, to the point X that I'm interested in. This point. Now, you know, the origin might be down here. Maybe here's the origin. So this is XQ. This is X. And if I take X minus XQ, I get R. All right, so the field due to one charged particle is Q R hat over 4 pi epsilon 0 R squared. Now, when you calculate it, it's usually easier if you rewrite that as Q R vector divided by 4 pi epsilon 0 R cubed. Because R hat just means R divided by the magnitude of R. R hat is the unit vector, parallel to R. And R is x minus xq. So I could write this as Q times x minus xq divided by 4 pi epsilon 0 times the length of x minus xq cubed. And if I'm given information about positions in Cartesian coordinates, this will be the easiest way to calculate the electric field. Now, if I have many charges, well, then the electric field is just the superposition. So suppose I had n charges, Q1, Q2, Q3 up to Qn. The electric field at a point x is just the sum over those n charges, Qi over 4 pi epsilon 0, x minus xi, over the distance x minus xi cubed. So if I had a system with, I don't know, 3 charges, and I want to know the position, I don't know, here, I would have a sum of 3 terms. I'd have the electric field from the first charge plus the electric field from the second charge plus the electric field from the third charge. I'd have to add those 3 field vectors as vectors. And I'd get some net vector, which the net vector would be the electric field of that system at that point. I could do that for any point. This could be some different point. Finally, the field due to an extended object. Well, I would have to view the object. Suppose I have an object shaped like a peanut, and it has a charge. Let's say its charge is Q. What's the electric field here? Well, I would divide the object into many small parts. I would divide it up into many small pieces. I would subdivide it or divide it into cells or something. And then each one of those I could regard as a point charge. And I could calculate the electric field from all of those point charges. So I'm dividing the object into an infinite number of infinitesimal parts and adding up the effects of all those infinitesimal parts. Well, you know, that gives me an integral. That'll be the integral. A little charge dq has an electric field dq over x minus x prime divided by 4 pi epsilon 0, x minus x prime cubed, where x prime is the position of dq. And then I have to add all the little parts, so that's an integral. I integrate over the charges. Or if I want to write it in terms of position, I could introduce charge density. So rho is the usual symbol for charge density in 3 dimensions. It's the amount of charge, dq, per unit volume, so divided by dV. If I have a small volume, dV, containing an amount of charge dq, then rho at the position of that volume is dq dV. dq divided by dV. So dq I can replace here by rho of x prime dV. dV will be d3x prime in Cartesian coordinates. So I have rho x minus x prime over x minus x prime cubed. Well, don't forget the constant, 1 over 4 pi epsilon 0, d3x prime. And if I had a 3-dimensional object, I would have to do this 3-dimensional integral. Sometimes I have 2-dimensional objects, like a disk, or 1-dimensional objects, like a rod, and then I can introduce the charge density for that system and integrate over the area of a disk or the length of a rod. There'll be examples like that in the ln kappa problems. That completes part 1 of the screencast, the theory. Now you should also watch part 2, examples. And after you've seen some example calculations, you should be ready to go on and try the ln kappa problems.